Last time, talking about the wave equation, and this time I want to talk about this general problem. You know, the vibrating string with fixed endpoints 0 to L and the compatible initial conditions. So remember, you've got the operator. So you're trying to solve the most general problem for the 1D wave equation is LU equals F with some initial condition. And what we have learned previously is that on the entire real line, we can solve LU equals 0 with initial conditions using D'Alembert's formula. We've learned that we can promote this to a solution from 0 to L by simply taking the odd extension of the initial conditions using D'Alembert's formula and then restricting the solution that we got then to the line. In the solution space, it's really like looks like an infinite rectangle. So in the domain of U, that's actually space-time, not just space. And finally, we learned about Duhamel's principle and the idea of convolution, and that allowed us to solve the problem that says, look, if you're on the entire real line and your initial conditions are 0 and you have LU equals F, then you can solve that problem by using a formula from the domain of dependence, or simply convolving F with the fundamental solution to the wave equation. And then if you wanted to restrict that to 0, from 0 to L, you can actually simply take the odd extension of F, and the argument will work. You know, an explanation similar to the argument that taking the odd extension of the initial conditions worked, like in that previous thing, a previous lecture, also shows that you really just need to take the odd extension of F, solve it with the convolution, and then restrict back to the interval from 0 to L. So I won't take too much time on that, but I'll point out that in principle, we've solved this problem for either LU equals F and 0 initial conditions, or for non-zero initial conditions and LU equals 0. That's where we are. So if you want to solve the general thing, the good news is that you can do it just using the information that we've got. And that is to say, like how do you solve this problem? So what you do is you say perhaps that W solves LW equals 0, but with W0x equals G and WT0x equals H. So we know how to solve that with D'Alembert's result, and say now that V solves LU equals F and V of 0x equals 0. And V sub t 0x equals 0. So solve these two problems individually like you know how to do. And then here's the really beautiful thing for linear equations. You can now just add them together. Then V plus W solves L of V plus W is going to be, you know, by linearity, this is going to be L of V equals F plus L of W equals 0. So L of V plus W equals F. It will solve the inhomogeneous equation automatically. And then what are the boundary conditions? Well, you can see if you take V plus W, restrict it to T equals 0, the answer will be G plus 0. So V plus W, 0x equals G, and now V plus W time derivative, 0x, will be equal to H. Again, just because taking the derivative is a linear operation, so that'll be equal to Vt plus Wt at 0x. So that's really kind of nice. So if you want to solve the general problem with general initial conditions, you have to go through this whole process where you're going to look at this problem first, extend f to an odd function, use like the Duhamel's principle or convolution. You'll solve this problem next, extend the initial conditions to an odd function, use D'Alembert's theorem. And take those two answers that you get and add them together, and then you'll get the solution to the general problem. So like from a theory standpoint, that completely characterizes the solutions to the wave equation. That's not to say that there isn't more to the story, because this method, while it does find the unique solution. Oh yeah, and by the way, these solutions are unique. So what do I mean by that? And I should also say that you have to include the hypotheses that we've been talking about. So for classical solutions, you want this to be C2 function, this to be C1 function, and you'd like this to be a continuous function. You can sort of keep track of it, because if two derivatives should be continuous, one derivative should be C1, no derivatives should be C2. So you're trying to eventually construct U that's C2. And the solutions are unique. And by that, I mean that if U1 and U2 solve this problem, they solve this problem here, I'll call this maybe problem star. So if U1 and U2 solve problem star, then U1 equals U2. That's what we mean when we say that a solution is unique. If you have two solutions, then they have to be unique. They have to be equal. And so, in other words, there are many solutions to LU equals F, but there's only one solution to LU equals F with these boundary conditions, and that's nice to know. And how might you solve this? Again, you're wanting to exploit the linearity of the equation, so you can consider the difference. Right, so the hypothesis of this theorem is, suppose that it's true that U1 and U2 already solve this equation. So already satisfy L of U1 equals F, L of U2 equals F, already satisfy these boundary conditions. If you apply the operator to the difference, then by linearity, this is going to be L of U1 minus L of U2. It'll be F minus F equals 0. And it'll also be true that the initial conditions are equal to 0 for the same reason as before, because when you restrict U1 and U2 to t equals 0, you get G both times, so their difference has to be G minus G equals 0. So this uniqueness argument really works for linear equations and does not work for nonlinear equations. Not to say that nonlinear equations don't have uniqueness, you would just need to argue a different way. Take it on a case-by-case basis. Okay, so now that you've got this, so now that you've got something that solves the wave equation with the 0 initial condition, this is going to imply that U1 minus U2 equals 0, which is exactly what you wanted to show. And certainly that makes physical sense. If you take a string at rest with no initial position, no initial velocity, let time run its course, of course it will stay at rest. How do you show that mathematically? Well, you can certainly just use D'Alembert's solution. There's a formula for it. That formula said, if you're a solution, this is your formula. That formula was, gx plus ct minus gx minus ct, so that's just a 0. And also the integral of h, which is integral of 0. So D'Alembert's formula would show you that the answer is 0 in that case. Yeah.
So on this side of the board, to solve for W, we would use D'Alembert, right?
That's right. And if you wanted to restrict it from, the question was like for solving for W, you would use D'Alembert's formula for that. And the answer is yes, that's definitely true. And furthermore, to get it from 0 to L, what you would, like if you were just given G and H from 0 to L, then you would take the odd extension and then use D'Alembert's formula, which applies to the whole real line. And then you'd restrict that formula back to 0 to L. And there's also some in this problem, there's also going to be some other initial conditions tacked onto that too, like 0 t equals 0 and L t equals 0, just because the endpoints of the string aren't supposed to move. But that's fine. When you take the odd extension, those conditions will percolate up and everything works out. Okay. So now that we've kind of closed off that story, and now that we've closed off that story, there was some discussion at the beginning of class about what about separation of variables? Like isn't everything separation of variables? Should we care about other things? Separation of variables is good, and there's another story behind that. We should care about both methods. The next thing that I actually want to do in this class, after working through with some examples with you today, is to talk about how you can also do this with separation of variables. And then you get into this interesting idea, which is that maybe you can solve something with a power series solution or with separation of variables and get an answer. You can also solve it with D'Alembert's formula and get an answer. By uniqueness, they have to be the same, which is very nice, I think. So you end up with different representations of the same solution. What's the benefit of, what's going to be the benefit of our separation of variables representation for the wave equation? It's going to allow us to focus on individual frequencies. So later on, when we learn about Fourier analysis, one way to think about that is, by taking different terms in the Fourier series, you can think of your solution perhaps as being like a sum of solutions of a particular frequency. And then you can identify solutions that have a particular frequency, which will be of interest to you. And in engineering later on, you can do these so-called filtering processes, which basically say, break up a solution into a sum of frequencies remove the frequencies that are very high or remove the frequencies that are very low, like high pass, low pass filtering. You see these things in like, what is it? Like Premiere Pro or Audition or things like that. And mathematically what's happening is you're kind of doing this Fourier decomposition and taking things out. So there's more to this story from a physical perspective in terms of representing these solutions that we know are unique, like in different ways, and then doing different things to that representation. And so that's a cool story, and we'll definitely get to it. But for today, we're going to garden. We're going to get our hands dirty. When I say we're going to garden, we're going to work the earth. We're going to actually do some solutions. So I don't think I'm going to illustrate necessarily methods of like adding together. I'm going to focus more on like solving this problem or solving that problem, since this is the one that's maybe less familiar to you. And in fact, let's just get right down to it. And it's not just solving the problem and working the integral. It's doing all these trig identities that kind of make the solution reasonable. And I don't know about you, but even just working through some examples in the text kind of threw me for a loop in terms of I actually had to go look up some trig identities and figure out what was going on and so on and so forth. And so if it threw me for a loop, maybe that means it's definitely good for me to come back and show it to you as well. So the first thing that I want to do, and maybe I'll make this partially a class exercise. I want to say, let us solve. LU equals F, so this L, and let's just take f of x equals sine of x, and let's solve it on the entire real number line. So let us not worry about the finite string or taking an odd extension of the forcing function. I mean, this is already, it's an odd function, so like you could consider this from like 0 to 1, and it's already extended, but let's just think of this as solving it on R. Let's take C equals 1 just for not dealing with lots of constants or units. And we'll take the initial conditions to be 0. So we'll take LU equals F, but with 0 initial conditions. So maybe I'll call this problem dagger or anchor, whatever. And so let's just so as not to write these down again. And in order to do this, it's really just an integration formula. So that like the answer is in principle, the answer is UTX equals integrate over the domain of dependence for TX and integrate the function sine x prime dx prime ds, right? Or you could also write this in the notation of last class as d star x. But I don't want to just do it in principle. I want to find an actual answer. And so I'll let you go for it for a few minutes. And this will be your opportunity to check your notes, to check that formula. Plug it in, do the iterated integral, see what you get. And if you're really ambitious, look up a trig identity and write your solution in a form that's as compact as possible. Absolutely. There's a factor of 1/2. Yeah, thank you. Oh, the domain of dependence for T and X. Yeah, you'll have to check out the video for the previous class. Yeah. But so I'll just go ahead and set up the integral then. So it's this integral. So that's the integral you're working. Okay, so after having given you some time to work, what you probably came up with as a first step is something like this. You probably did the first iterated integral, right? So you would note that the antiderivative of sine is negative cosine, and then just evaluate at the endpoints. So this is something like what? Cosine of x minus t plus s minus cosine of x plus t minus s. And then you want to evaluate that with respect to ds. So is that reasonably close? And then for your next step, this is not so bad to integrate. So you could do a quick substitution, or integrating with respect to s. The antiderivatives are sine, and yeah, actually you can just straight up write it down. Well, actually, I'm still not going to though. But you could just write down the antiderivatives, some sine of this minus sine of that, evaluate at s equals 0 and s equals t. But the reason why I wanted to give you some time to do it by yourself is because I kind of want to point out that you can write these solutions in lots of different ways. So for instance, I've got here my handy list of trig identities that I printed off from Wikipedia last night, just so I won't get confused and write something down the wrong way. I'll notice here we've got a difference of cosines. So you may already have all of these angle difference, like some formulas memorized. I don't really I don't really have them memorized, so I'll kind of read off of a formula. And so like if you take cosine of a difference minus cosine of a sum, right? I'll go ahead and write down the formula. So this is 2 sine theta cosine phi, or 2 sine theta sine phi. Excuse me, that's cosine. Theta minus phi minus cosine. Theta plus phi. And so what does that equal to? I think we can take
2 sine x times sine t minus x.
what's your theta and what's your phi?
My theta is x and my p is t minus
So yeah, this gives me theta minus phi, and this gives me theta plus phi. All right, so that sounds good. And so the 2's will cancel, and I'll be left with sine of x times sine of t minus s. Yeah, I guess I heard you say t minus x instead of s, so I got a little confused. So you could also just do this integration with respect to s, and so now you'll end up with sine x, and then, because that's kind of like a constant with respect to s, and then what do you get? Minus cosine? Well, yeah, I was going to do that separately, but that's right. And then dividing by -1, and then going from 0 to t. And so plugging in s equals t, we get sine x cosine 0. And then plugging in s equals 0, we get sine x cosine t. So that's your nice solution to this problem, to the wave equation for that particular forcing function. If you know this, I won't pull it up on the Zoom call now for sake of time, but if you know this GeoGebra program, they have like a little 3D graphing utility that I encourage you to plug the graph in, and you can sort of like see the rolling waves, and it's nice. Let's kick it up a notch. Oh, and yeah, and if you just did this organically, you could also do the trig formula at the last step, and again, arrive at this. You'd get sines, and you'd use the corresponding difference formula for sines to arrive at this step. Let's do another problem. So let's take same setup, but new forcing function. And so let's take f of tx to be equal to cosine of omega times t times sine of omega naught times t with omega naught equal to pi over L. Let's take C equals 1. As before, G equals H equals 0. And this time I really do want to work on the string going from 0 to L. But also this time, notice I've got my forcing function. It's already an odd extended function with period. I've got it worked out. So with period to L. Omega is a fixed parameter that you get to choose. What do they call it? It's a frequency. It has a physical name. We have this fixed omega naught, and then separately, I'm introducing a new frequency. So this is a frequency given by the force, and this is sort of a frequency that's determined by the length of the string. Yeah. So can we solve this problem? And this is example 4.8 if you want to track through with that, but the details are pretty skimpy. So first, let's just go ahead and write down our base formula. So just by convolution or by Duhamel's principle, so that's what we get at first blush. And quite similar to the last time, you can integrate this with respect to x prime, right? And then cosine omega s becomes a constant with respect to that variable. So you're just integrating this and then plugging in the conditions. And so here what you get as before, I get cosine omega times s multiplied by cosine omega naught times x minus t plus s minus cosine omega s cosine omega naught times x minus t minus s ds. So I'll let you verify it yourself.
Is the variable in the side supposed to be an x prime?
Yes. Oh, like instead of, this should be, that's incorrect. So what I want to do is sine omega naught of x. This is a frequency associated to the string, and so we should have a spatial variable there with it.
And the first integral, with the top value as plus t minus s.
Yeah, makes more sense.
And on the dimensions for omega naught
Okay, thank you. So this makes it x minus t plus s, and then x plus t minus s. Yeah, thank you. But now it's all good. Okay, cool. And so now what I would say is, Similarly, so factor out this cosine omega s and use this angle difference formula to reduce this integrand. And I'll actually give you a minute to work on that. So instead of showing that calculation again, since we kind of did it for the model with forcing function equals to sine, I'll show you what I got. So for this, I got sine of omega naught x, which I pulled out of the integral, divided by omega naught, integral from 0 to t, sine of omega naught t minus s, cosine omega s ds. So in this case, the book and I land at the same place. But if you're wondering where that intermediate step comes from, it's from that difference formula. So take a moment and see if you disagree or you have any questions. I mean, that formula is now erased, but it was what? Like a difference of cosines turned into like sine of 2 sine theta cosine phi. And so the 2's canceled out. That's going to be coming from this integration. So I think that was already there. Yeah, yeah. If I just do these calculations, I'll make so many typographical errors. But if we do them together, it kind of works out a little bit nicer. So, but certainly, I hope that's kind of transparent now. The cosine omega s stays the same, and here's the like theta and phi. The 2's canceled from that identity, and so that makes sense, right? Omega naught x, and then you're either adding t minus s or subtracting t minus s. And it works out. And so then like the next step in the text is kind of ambitious. Before just kind of going forward, maybe I'll ask the class, does anybody see, like off the top of your head, how would you do this integral? Yeah, I think you kind of want to go the other way. Like it seems kind of silly because we just turned this difference into a product. But part of the reason for that was so that we could factor out this term. And now we're left with a different product that it's hard to integrate because these constants are different. But if we turn it back into a difference, then we could integrate it. And you can kind of pick your poison, but because this is going to be like 2 sine of something, cosine of something. So this is basically 2 sine theta cosine phi, right? And I'll just use my little Wikipedia sheet. This was the same one we had before, right? Well, actually, maybe because it's cosine instead of sine, it's a little bit different, but it's same idea. So this one becomes, I'll write the equality below. This one becomes sine theta plus phi plus sine theta minus phi. So then I'll give you a minute. Please fill in the integrand using that formula. And eventually there's going to be 2 cases, and we're going to end up in the case here where omega is not equal to omega naught, because eventually I want to divide by omega minus omega naught. Let's just assume for the moment that these 2 things are not equal. Yep. Oh, I just multiplied and divided so that this would be easier to plug into the formula.
Oh, you just, wait, I think it's asking about it all the way through to the next step.
Oh, I see. Yeah. Right. Thank you. So yeah, let's kind of straightforwardly plug it in, and taking sine of theta plus phi plus sine of theta minus phi ds. And so this you can now integrate, right? So you get minus cosine and what are you dividing by? Isn't it s times, or isn't it like s times omega minus omega naught? Can check my constants there, and then minus cosine and then we'll get on the bottom here minus omega plus omega naught. And of course, these negative signs will kind of cancel. And no longer ds. And in fact, we're evaluating from 0 to t. So this is kind of why you need 2 cases. Like these 2 things are equal or they're not. If they're not equal, you can form this antiderivative. If they are equal, you can condense this integrand and integrate it kind of easier. You don't. So if they're equal, do it here. And then you'll get a different integrand. Yeah. So the answer to the problem will just change depending on whether they're equal or not. So you want to divide it up into 2 cases. When they're equal, this is this classic example of resonance from ODE. You'll get a linear factor of t in this integral. If they're not equal, then we'll see what we get. perhaps. And so I kind of want to combine these back together using like an angle difference formula, although the problem is I have different denominators here. So how do you kind of, yeah, you kind of fix this common denominator business. And yeah, it's some algebra, but first I guess we can kind of plug in t and 0. And plugging in s equals t gives me omega s. Cosine of minus omega s, which is just cosine of omega s. Omega plus omega naught. And I'm subtracting from this, plugging in s equals 0, right? So plugging in s equals 0 now gives me minus cosine omega naught times t divided by omega minus omega naught, and then plus with s equals 0 giving me cosine omega naught t over omega plus. Yes. So I'm taking s equals t, so these should be t's. Thank you. So fine, and let's see if we can reduce this and do common denominator at the same time. So I'm going to factor out I'm going to divide by 2 omega naught, and then the common denominator is, I'll call it omega squared minus omega naught squared. And we'll end up with, so I have to multiply this by omega plus omega naught, right? And then here, omega minus omega naught. More terms, so minus minus is plus, and I'm getting omega plus omega naught. And then minus cosine omega naught t, and it's omega minus omega naught. Okay, and so what? Here's minus cosine omega t times omega, and plus cosine omega t times omega, so that is 0. Here's plus cosine omega naught t times omega. Here's minus cosine omega naught t times omega. Those terms sum up to 0. What about the other terms? I have minus 2 cosine omega t times omega naught. I have plus 2 cosine omega naught t times omega naught. So that's actually amazing that that worked out. So the 2's come out and cancel. The terms with omega are 0. So you end up with sine omega naught x times omega naught divided by 2 omega naught omega squared minus omega naught squared times what? It's I'll do the positive one first, so that's cosine omega naught t minus cosine omega t. Did I get that right? And then the omega naughts cancel.
Can you explain that definition?
So there are 1, 2, 3, 4, 5, 6, 7, 8 terms in this expression. 4 of those terms are 0, or 4 of those terms evaluate to 0 because the omegas always come with corresponding positive and negative signs. So now let us look at the terms that are multiplied by omega naught. And I get cosine omega t with a negative sign, cosine omega t with a negative sign times omega naught. And in fact, these other two terms have an omega naught, which I then factored out and canceled. And so since this was twice negative omega t, yeah, so there's an extra 2 here that cancels with that. Since this was twice negative cosine omega t, that goes here. And the other 2 are now twice cosine omega naught t. So the 2 factors out of everything. The omega naught factored out of the 4 remaining terms. The 4 terms against omega cancel each other out. And this was the common denominator from before. And so I know I'm a couple minutes over, and I apologize for that, although this is not like a place where you pick up right in the middle of the next time. So, and we're basically finished. So this answer for uxt looks like this. And in fact, if you track along in the example, they kind of, and I don't think they're wrong to do this in the book, but they kind of just skip straight from omega squared minus omega naught squared, thank you. They kind of skip straight to the answer and skip all of the trig formulas and you know, so on and so forth. But since you're going to be undoubtedly confronting problems like these on your homework, I thought I'd kind of prove to you that you really can do these calculations, but you kind of need this judicious use of these trig identities. And the other case, when omega is equal to omega naught, it's actually considerably easier than this one, so like I won't show it in class, but what you do is before performing the integration that puts this on the denominator, simply equate those two things, and you'll get you'll get a reduction in the argument to the trig functions, and you'll see that you can actually quickly integrate that. You get a really different solution. You get something. In one they do, in the other it's doubled. Yeah. The question was, you know, like do the s's disappear in the integrand? And so you end up with basically something multiplied by t, so giving you a linear growth in amplitude with time, corresponding to the so-called principle of the forcing frequency being equal to the resonant frequency of the string. Okay, so fine. Next class, instead of proceeding to the multidimensional version of wave equation, we'll actually go straight to Helmholtz equation, eigenvalues, the classic separation of variables, and some of those physical properties. So thank you everybody for your time and attention, and I'll see you on Monday.